Okay, let's kick things off with a look at data engineering. Simply put, it's all about building the systems that allow us to take raw data and turn it into something useful. It's like creating the infrastructure behind all those amazing insights you hear about in business. Data engineers are responsible for collecting data from everywhere: databases, API, even files. They then clean it up, transform it into a usable format, and organize it securely within data warehouses or data lakes. Essentially, they ensure that the right information is available at the right time for everyone who needs it. Okay, let's clarify what each of these roles actually does. Data engineering is all about building and maintaining the systems that allow us to get data. Essentially, it's about creating the pipelines that bring information into a usable format. Data scientists are focused on using that data to uncover hidden insights and build predictive models. And finally, data analysts take those insights and turn them into actionable recommendations for businesses. Essentially, they use the roads built by engineers to discover valuable resources. Okay, let's break down the life cycle of data engineering. It's all about getting your data from wherever it lives to where you need it, and ensuring it's good quality along the way. First, we start with discovery, figuring out what data sources exist and how trustworthy they are. Then we design a solid schema, like a blueprint for our data. Next up is ingestion, pulling the data into our system, often using ETL or ELT processes. After that comes transformation and cleansing, making sure it's accurate and consistent. Finally, we choose the right storage solutions, think data warehouses or data lakes, and manage them effectively to keep things running smoothly. Okay, let's talk about getting the data into our systems. That's data ingestion, basically loading information from all its different places into one central location. There are several ways to do this, and it really depends on where your data is coming from and how quickly you need it. We often use batch ingestion, which is like collecting everything at once, think daily reports. Then there's stream processing, which deals with constantly flowing data, like social media feeds. And finally, change data capture, allowing us to keep up with updates in real time. Okay, so when we're talking about processing data, there are really two main ways to think about it: batch and stream. Batch is like taking a big snapshot of all your information, maybe every day or week, and then doing some heavy lifting on that entire data set at once. It's great for things where you don't need immediate answers, like generating those daily sales reports. On the flip side, stream processing is more like constantly watching data as it comes in, reacting to new information as it happens. Think of a real-time dashboard. If something changes, you want to see it instantly. This approach is really useful for things like spotting fraudulent transactions or analyzing data from sensors, basically anything where speed is critical. Let's talk about data lakes. Think of them as huge, flexible storage areas for all types of data, structured like spreadsheets, semi-structured like JSON files, and even unstructured things like images or videos. Unlike traditional databases that require you to define the structure upfront, with a data lake, you apply the structure when you actually need to use the data. This flexibility is key. We often build these on cloud storage solutions, which are fantastic for scaling and keeping costs down. Now, there's not just one way to set up a data lake. Architectures like lakehouses, Lambda, and Kappa offer different approaches depending on how you want to analyze your data and what kind of processing you need. Let's talk about data warehouses, and specifically how they differ between OLAP and OLAP systems. Think of your online banking. That's a classic example of OLAP. It's constantly handling individual transactions in real time. You're making purchases, transferring funds, updating information, all happening quickly and frequently. Now, contrast that with looking at overall sales trends over the past year. That's where OLAP comes in. These systems are designed for analyzing large datasets to identify patterns and insights. They handle less frequent, complex queries, focusing on understanding what has happened rather than recording what's happening right now. Let's talk about modern data warehouses. They are a huge shift from the old way of doing things. Think of them as supercharged data centers in the cloud, like Snowflake, Google BigQuery, and Amazon Redshift. These aren't your grandpa's data warehouses, they are designed to be incredibly scalable and easy to use. Snowflake stands out with its unique architecture where compute and storage are separate, allowing for really flexible scaling. BigQuery is a serverless option, so you don't have to worry about managing anything. And Redshift lives within the Amazon ecosystem, offering great performance. Each one has its strengths. Understanding these differences will help you choose the right tool for your data needs. Okay, let's talk about how we move data around in data engineering, specifically the difference between ETL and ELT. Think of ETL as a classic process. You first pull your data from all sorts of places, databases, applications, even files. Then you clean it up, reshape it, and do any necessary calculations in an intermediate area like a staging database. Finally, you load that transformed data into your main target database. It's great for smaller projects where you want tight control over the transformations. However, it can be slow, especially if you have a lot of data to process. Now, ELT is more modern. With ELT, you just pull your data and dump it straight into your final destination, your data warehouse. The real transformation happens inside that data warehouse using its own powerful tools and resources. This means faster loading times and the ability to handle massive amounts of data. It's perfect for big data projects where scalability is key. The main difference boils down to where you're doing the heavy lifting. ETL does it beforehand, ELT does it later. Let's talk about ETL tools. They are basically the workhorses of data engineering. We've got a few big players here. Apache NiFi is really powerful for building complex flows, kind of like Lego bricks for your data. Then there's Talend, which provides a complete platform with a visual interface that makes things easier to manage. Informatica is a solid choice if you need something scalable for larger organizations. Airbyte is gaining popularity because it's open source and super easy to get started with. And finally, Fivetran specializes in automating the whole process with pre-built connections. It's like having a data pipeline built for you. Let's talk about how we get all these different pieces of our data pipelines working together smoothly. Orchestration is essentially the conductor of your entire data workflow. It makes sure everything runs in the right order, even if things go wrong. We've got three main players here: Apache Airflow, Luigi, and Prefect. Airflow is a really powerful platform for complex workflows with lots of dependencies. Luigi is simpler to get started with, especially if you're focused on batch processing. And then we have Prefect. It's a more modern approach that makes using code to define your workflow much easier. Okay, let's talk about how we organize our data for efficient analysis. It's all about data modeling. We have three main approaches: the star schema, the snowflake schema, and the data vault. The star schema is super straightforward. You've got your core business events in a central fact table, with dimension tables giving context around them. It's really easy to understand and makes queries run quickly. Next up we have the snowflake schema. It's similar to the star but takes things a bit further by breaking down those dimensions into smaller, more specialized tables, which reduces redundancy but could slow things down a little when running complex queries. Finally, there's the data vault model. This one is designed for really long-term data and keeping track of changes over time. It's a bit more complex to set up initially, but it offers fantastic flexibility. Okay, so let's talk about SQL. It's absolutely essential for data engineering. We'll start with the basics: select, from, where, and order by. These are your core tools for retrieving information from databases. Then we move on to more advanced techniques like joins, which let you combine data from multiple tables. Subqueries: these can be really helpful for filtering and aggregate functions like sum and count. Finally, we'll explore window functions that are extremely useful for doing calculations across sets of rows. Let's talk about NoSQL databases. These are a different approach to storing data compared to the traditional SQL systems we often hear about. They're designed to handle massive amounts of information, especially when that information isn't neatly organized into rows and columns. Think of them as more flexible, easier to scale solutions for modern applications. We'll quickly cover some popular types like MongoDB, Cassandra, HBase, and DynamoDB, each with its own strengths. Okay, let's talk about relational databases. These are absolutely fundamental to data engineering because they provide a structured way to store and manage our information. We have some big players here: MySQL, which is really popular for websites; PostgreSQL, known for being super powerful and reliable; Oracle database, often used by large companies needing serious scalability; and SQL Server, Microsoft's offering that works great with Windows systems. Think of them as the strong foundation upon which a lot of our data pipelines are built. Okay, so when we talk about data engineering and scaling up our pipelines, a really important piece of the puzzle is distributed systems. Think of it like this: instead of cramming everything onto one powerful server, which can get expensive and eventually hit limits, we spread the work around across many smaller machines. We do this through things like sharding, where we break the data into pieces and assign each piece to a different machine. And for safety, we often replicate the data so that if one machine goes down, we still have copies available. There's also the tricky question of consistency. How quickly does everyone see the changes? It's about balancing speed with reliability. Okay, so let's talk about how we deal with really big data sets. We're going to dive into partitioning and sharding. These are like the secret weapons for making your databases run smoothly when they get huge. Partitioning is essentially breaking up a large table into smaller, more organized chunks, much like folders on your computer. Sharding takes it a step further by spreading those chunks across multiple servers, so you can process data in parallel and handle even bigger volumes. When choosing your partitioning key, think about how people will be searching for information. You want to distribute the data evenly and make sure common queries are fast. And don't forget about replication. Having copies of your data ensures everything stays running smoothly even if one server goes down. Okay, let's talk about keeping our data safe and always available. That's what replication and high availability are all about. It's super important because if your database goes down or you lose data, it can seriously mess up your business. There are a few key ways we handle this. We often use master-slave setups where one database is the main source of truth, and copy slaves keep those changes updated. This lets us offload read requests to the slaves, making things faster for users. Then there's multi-AZ deployment. Think of it like having a backup in a different location within your region. So if something happens in one area, you can quickly switch over. And finally, sharding helps us handle really big datasets by splitting them up into smaller pieces. Okay, so let's talk about what actually makes up a big data system. It's not just one big server. First, we have the data sources. That's where all this information starts, coming from lots of different places like websites, apps, and even sensors. Then it needs somewhere to live. So we use cloud storage solutions like Amazon S3 or Azure Blob Storage to hold these huge amounts of data. Next up are the processing engines. Think of them as the data workers: Spark, Hadoop, Flink. They're all about transforming and analyzing that data. Finally, you'll often see data warehouses or lakehouses like Snowflake or BigQuery, where we store this analyzed information ready for reporting and insights. Okay, let's talk about Hadoop and HDFS. They're absolutely critical for working with big data. Hadoop is essentially a whole toolkit. It's not just one program. It provides the way to store and process massive amounts of information. The key players are MapReduce, which handles how we actually do the processing, Yarn, which manages all the resources in our cluster, and HDFS, that's the storage part. Think of HDFS as a giant, incredibly reliable hard drive spread across many computers. It breaks files into smaller blocks and copies those blocks around to make sure there's always a backup. It uses name nodes to keep track of where everything is located, and data nodes actually hold all that data. Okay, let's talk about some of the foundational technologies you'll encounter when building data pipelines. First up is Apache Spark Core. It's essentially a super fast engine for processing massive amounts of data in parallel. Think of it as a really efficient way to move and manipulate information across many computers. Then we have Spark SQL, which lets us use standard SQL queries to work with our data, making it familiar if you've come from a relational database background. Finally, we're looking at Spark Streaming. This is what allows us to process real-time data as it comes in, like sensor readings or social media feeds. It uses micro-batches and windowing operations to give us meaningful insights quickly. Okay, let's talk about Apache Kafka. Think of it as a central nervous system for your data platform designed to handle massive amounts of information in real time. It's built around the concepts of topics, which are like categories for messages, partitions, which divide those topics for speed and efficiency, brokers, which are the servers that hold all this data, producers who push the messages in, and consumers who pull them out. Kafka's really powerful because it's designed to scale incredibly well, offers built-in fault tolerance so your data isn't lost, and lets you get those insights immediately from streaming information. Let's talk about message queues. They are absolutely essential for building robust and scalable data pipelines. Basically, they act as a middleman like a post office between different parts of your system. Producers send messages to the queue, and consumers pick them up when they are ready, even if the producers are busy or offline. RabbitMQ is a really popular choice because it's mature and adaptable, while Apache Pulsar shines with its high performance and cloud-native design. Using message queues ensures everything works together smoothly, handles unexpected delays, and allows your data pipelines to scale as your needs grow. Okay, let's talk about how we actually store data in a way that computers can understand really efficiently. When you're dealing with big data sets, and trust me, you will be. It's not enough to just have the raw information. We need to consider how it's represented and structured. Serialization formats are key here. They determine how we encode data into a binary or text-based format for storage and retrieval. Factors like schema evolution, easily adapting as your data changes, compression, query performance, how quickly you can get at the data, and even how well different systems can work together all come down to choosing the right serialization format. We've got some popular options like Avro, which is fantastic for dealing with changing schemas. Parquet and ORC are really good for analytical workloads because they're columnar formats. JSON is super common for configuration or when you need something human readable, and Protobuf offers a very efficient binary representation often used in microservices. Choosing the right format depends on your specific needs. Okay, so let's talk about data validation and quality checks, really important parts of getting your data right. Think of it like a health check for your information. We need to make sure our data is accurate, consistent, and complete, because if that's not the case, any insights we get from it could be wrong. It's about spotting errors early on, building trust in the data itself, and preventing bad decisions based on flawed information. We check things like data types or numbers actually numbers. Are dates formatted correctly? We also look for out-of-range values, missing data, and any inconsistencies between different sources. Okay, let's talk about ensuring your data is handled responsibly. Today we're diving into data governance and compliance, specifically looking at GDPR and HIPAA. GDPR applies if you're dealing with personal data of people in Europe. It's all about being transparent, fair, and protecting their information. HIPAA, on the other hand, focuses on safeguarding health-related details. Think patient privacy. It requires a lot of security measures to keep sensitive PHI safe. To make sure you're compliant, you need to map out where your data lives, have clear privacy policies that people can understand, and put in place strong security controls. Let's talk about data catalogs. Think of them as a central index for all your company's information. They help you find exactly what you need, understand its meaning, and trust that it's reliable. We'll look at two popular choices: Apache Atlas, which is great for managing metadata across many different systems, and Amundsen, specifically designed to make data discovery easier within Snowflake. Essentially, they both tackle the problem of having too much data and not knowing where it is or what it means. Now we're moving on to discussing how to implement data governance policies and adding more details, enriching our metadata to build a truly effective catalog. Okay, let's talk about managing our data schemas. Think of the schema as the structure of your data warehouse. It tells everything where to live and how it should be organized. We need to actively manage that structure. That means keeping track of changes using version control, documenting what we're doing, and making sure new data always follows the rules. Schema evolution is all about adapting to change. As our business grows and things shift, our schemas have to evolve too. We can add new fields, but sometimes we need to remove old ones. It's a delicate balance. Good schema management and evolution practices help us maintain data quality and make sure everything stays organized. Okay, let's talk about data versioning and lineage. Think of data versioning as track changes for your datasets. It keeps a record of every single modification you make, so you always know exactly what happened to the data at any given time. This is super important because it prevents accidental errors, lets you easily roll back if something goes wrong, and helps with debugging. We use things like Git or specialized tools like DVC to manage this. Now, data lineage is all about tracing the journey of your data. Where did it come from? What transformations were applied to it, and how's it being used? It's essentially a map showing all the dependencies between different stages of your data processing pipeline. Understanding lineage helps you monitor quality, quickly find issues, and figure out how changes ripple through your systems. Okay, let's talk about column-oriented databases. They are a really important shift in how we handle big data. Think of it this way. Traditional databases are like reading a book row by row. But when you need to find the average age of all the people in that book, you have to red asterisk every asterisk single line. Column-oriented databases, like ClickHouse and Druid, store information vertically, like stacking all the ages together, then all the names, etc. This makes it incredibly fast for analyzing large datasets because they only need to pull out the specific columns you're asking about. They are especially useful when you're running complex queries that involve lots of aggregations and calculations. Let's talk about streaming data. Traditional ways of handling information often take a while, but with the rise of real-time applications, we need something faster. That's where streaming frameworks like Apache Flink and Spark Streaming come in. Flink is really designed from the ground up for continuous streams, making it excellent for things that need super low latency, think fraud detection or immediate alerts. Spark Streaming takes a slightly different approach, building on Spark's existing capabilities. It breaks down streams into small batches to process them efficiently, which makes it a good choice if you're already familiar with the Spark ecosystem. They both offer amazing solutions, but choosing the best one depends on exactly what your project needs. Let's talk about how we process massive amounts of data. Traditionally, Hadoop MapReduce was the go-to solution. It works by breaking down a big job into small amount of tasks that spread across many machines, then shuffling and sorting those results before combining them in reduced tasks. Now, Apache Spark has become hugely popular because it's often much faster. It can do a lot of its work in memory instead of constantly reading from disk. Think of it like this. MapReduce is like a slow but reliable truck, while Spark is a super fast sports car. Both get the job done, but one gets there quicker. Okay, let's talk about cloud data platforms. We're looking at the big three: Oz, Google Cloud Platform, and Azure. Each offers a suite of services designed for managing and processing your data in the cloud. AWS is really popular and provides things like S3 for storage, Glue for ETL, and Redshift for warehousing. GCP focuses on BigQuery for super-fast analytics, Dataflow for complex transformations, and Dataproc to run Hadoop jobs. And Azure has Synapse Analytics, which combines data warehousing and big data processing, plus services like Event Hubs for streaming data in. Okay, so let's get down to brass tacks. Where do we actually store all this data? We need robust solutions that can handle massive amounts of information efficiently. Amazon S3 is a really popular choice. It's super scalable and excellent for things like images or logs. Azure Blob Storage does the same thing but lives inside Microsoft's cloud environment, and Google Cloud Storage provides similar capabilities from Google. Each has its strengths, so picking the right one depends on your overall setup. Okay, let's talk about caching, a really important part of building efficient data pipelines. Basically, we're trying to avoid hitting our slower back-end systems repeatedly. Caching is like having a quick access memory for frequently requested data. Two popular choices are Redis and Memcached. Redis is more powerful. It has features like persistence, which means it can save your data even if the server crashes. Memcached is simpler and incredibly fast, great for basic key-value caching. It's all about finding the right balance between complexity and performance. Think carefully about what you need to cache and choose the tool that fits best. Okay, let's talk about infrastructure as code. Think of it like this: instead of clicking through a bunch of menus in the Cloud Console to set up servers and databases, we write code that tells the system exactly what we want. Tools like Terraform and CloudFormation help us do just that. Terraform works across multiple cloud providers, OS, Azure, Google Cloud, using a special language called HCL. And AWS CloudFormation is their own native solution, using YAML or JSON. Both approaches make our infrastructure more consistent, easier to manage, and less prone to human error. Okay, let's talk about cloud-native data engineering. Basically, it's a shift away from setting up complex on-premise data systems and instead using the power of the cloud to build our data pipelines. We're talking about things like serverless computing, letting the cloud provider handle running your code when needed, containerization to ensure consistency across different environments, and really leaning into managed services provided by cloud providers like AWS, Azure, or Google Cloud. This makes it easier to manage everything, scale up quickly if we need to, and ultimately, it can be more cost-effective than maintaining a huge amount of hardware ourselves. Okay, let's talk about serverless data pipelines. They are a really efficient way to move and transform your data. Basically, instead of managing servers yourself, which can be quite a pain, you use services like AWS Lambda or Azure Functions. These platforms automatically scale as needed, so you only pay for what you actually use. It's super helpful when you have fluctuating data volumes. Think about it. You write small pieces of code that do specific tasks, and the cloud provider handles everything else. It's a great way to reduce operational overhead and keep costs down. Okay, let's talk about data lake as architecture. It's a really powerful way to handle your data. Think of it as the best of both worlds. It takes the flexibility and scale of a traditional data lake where you store all your raw data in its original form and combines it with the reliability and structured querying capabilities of a data warehouse. It's built on something affordable like cloud storage, so it's super cost effective. Key to this is having a metadata layer that tells us what's in our data lake and how we can make sense of it, along with the powerful compute engine like Spark for Databricks SQL to actually do something with all that information. And importantly, good governance and security are built in from the start to keep everything organized and safe. Let's talk about ACID transactions in the context of big data. Traditional databases are fantastic at ensuring all operations either succeed completely or fail completely, maintaining a consistent state. However, when dealing with massive datasets processed across many machines like those found in Hadoop and Spark systems, things get trickier. These distributed environments often lean towards eventual consistency, meaning updates might not be immediately visible everywhere, prioritizing speed over absolute guarantees. To address this, we employ techniques like solvers, which break down complex transactions into smaller steps, two-phase commit, a coordination mechanism for distributed operations, and compensating transactions, essentially actions to undo changes if something goes wrong. It's about finding the right balance between consistency and performance in these large-scale data environments. Let's talk about how we use real-time analytics in the world of data engineering. It's all about getting insights immediately, not waiting for batch reports. Think about fraud detection, spotting dodgy transactions as they happen, or monitoring equipment with IoT sensors to predict when something might fail before it does. Personalized recommendations on websites and apps are another great example, adapting content based on what you're doing right now. Even live sports analytics rely on this, tracking every player's movement during a game. And of course, supply chain management benefits hugely from real-time visibility. The key to making all this work is having robust data engineering pipelines that can handle the flow of data at speed using tools like Kafka and Spark Streaming. Okay, let's talk about keeping your data safe. Data security is a really important part of the entire data engineering process. We want to make sure that only authorized people can access sensitive information. First up, We have encryption, essentially scrambling the data so it's unreadable without the right key. Then we implement role-based access control, which means giving each person or group exactly the permissions they need and nothing more. And finally, let's discuss Kerberos, a sophisticated system that helps us verify who is logging in securely. It's all about layered security to build a robust defense for your data. Okay, let's talk about a really important concept in data engineering, role-based access control. Basically, it's all about making sure the right people have access to the right things. We start by defining different roles like data analyst, data engineer, or database administrator. Then, we give each role specific permissions, dictating what they can do with data and systems. Finally, we assign users to those roles based on their jobs. It's a powerful way to keep sensitive information secure while still allowing people to do their work efficiently. Let's talk about distributed query engines. Think of these as powerful tools that let you pull data from all sorts of places: your data warehouse, your data lake, even different databases, and ask questions of it all as if it were in one single location. They're built to handle huge amounts of information and use standard SQL, so it's familiar territory for most data professionals. We have a few popular options like Presto, which is great for speed and ease of use, Trino, which is a strong open source alternative with excellent performance, and Dremio, that specializes in optimizing data lakes on the fly. Essentially, they're helping us bridge the gap between where our data lives and where we need to analyze it. Okay, let's talk about keeping your data safe, specifically backups, archiving, and recovery. The first thing to understand is that you need a solid backup strategy. Think of the 3-2-1 rule: 3 copies of your data on 2 different types of storage media, with 1 copy stored offsite. We typically do this with full backups, which capture everything, alongside incremental or differential backups, which only capture changes since the last time. Next up is archiving. This isn't about quick access, it's for long-term retention, often used for compliance reasons. We can use cloud services designed specifically for archival storage to keep costs down. Finally, and just as importantly, you need a recovery plan. This means having documented procedures that outline how quickly and reliably you can restore your data from backups. It's absolutely vital to regularly test these procedures. Don't rely on the hope they work. Okay, let's talk about keeping your data pipelines running smoothly. Monitoring is all about watching those key numbers: how long things take, how often they fail, and how much data is flowing through. Tools like Prometheus and Grafana give you a clear picture of what's happening in real time. We focus on pipeline health, checking if everything runs correctly, monitoring data quality to make sure it's accurate and consistent, and keeping an eye on resource usage to spot potential bottlenecks. And when something goes wrong, a delay and error alerting systems kick in automatically, so you can jump in and fix things before they cause bigger problems. Let's talk about monitoring our data pipelines. It's a really important part of data engineering. We need to understand how things are performing, so we focus on collecting key metrics like latency, error rates, and resource usage. Prometheus is a fantastic tool for this. Think of it as a time series database that constantly scrapes information from our systems using HTTP. It's incredibly flexible. You can write queries to get exactly what you need. And then, Grafana takes those collected metrics and turns them into beautiful, interactive dashboards where we can easily identify any issues or trends. It even lets us set up alerts so we're notified automatically if something goes wrong. Okay, let's talk about how we can make data pipelines much faster by using parallel processing and distributed computing. Imagine you have a giant spreadsheet. Trying to analyze it on one computer can take forever. Parallel processing breaks that big task into smaller pieces that different computers can work on at the same time. Distributed computing then takes this a step further, spreading those pieces across an entire cluster of machines. Tools like MapReduce help us do this systematically, and technologies like Spark and Kafka let us handle really large volumes of data in real time, perfect for things like live dashboards. Okay, let's talk about keeping our data pipelines running smoothly, especially when things go wrong. We're diving into 2 really important concepts: speculative execution and fault tolerance. Speculative execution is like having a backup plan before trouble even arises. It involves anticipating potential problems and getting alternative routes or steps ready to go. Think of it as an if this, then that strategy built right into your process. Now, when those inevitable failures do happen, and they will, fault tolerance mechanisms step in. These are things like automatically retrying failed operations, duplicating key components so you have a backup, and regularly saving the state of the pipeline. So if something goes sideways, you can just pick up right where you left off. Putting these two techniques together is what really builds resilient data pipelines, ones that can handle unexpected issues without sacrificing your data's integrity. Let's talk about data skew. It's a common challenge in big data engineering. Basically, it means some columns have way more data than others, often a long tail of extreme values. This can really slow things down when you're working with the data, especially during queries or aggregations. It can be caused by all sorts of things, like a few users generating most of the activity, or problems with how data is logged. Because of the skew, performance suffers, your queries take longer and you use more resources. The good news is there are ways to tackle it. We can pre-calculate some aggregates at the source, taking representative samples, or even group similar values together using techniques like bucketing. And don't forget about optimizing data types to make things run smoother. Okay, so let's talk about how we actually change data. Data transformation is a really important step. It's taking raw information and making it ready for use. We've got three main tools here. SQL, which is great for working with databases. PySpark, used when you have a lot of data that needs to be processed quickly. And Pandas, perfect for smaller datasets and getting a good look at your data before doing anything else. Let's talk about why Python is so crucial in data engineering. It's incredibly easy to learn and read, which makes it a lot easier to build and maintain complex data systems. Plus, there are tons of powerful libraries like Pandas for working with data frames, NumPy for numerical calculations, PySpark for handling massive amounts of data, and that's just scratching the surface. Python really shines because of its huge community. If you ever get stuck, you'll find plenty of support. Now, we will dive into some core concepts to build your understanding. Okay, let's talk about how we actually get data from different places. Think of API as doorways to all sorts of data sources. There are a few main types. REST file API are super popular because they're simple and widely used. GraphQL is great for getting exactly the data you need without wasting anything, and SOAP is an older technology that's still found in some systems. Now, when it comes to actually bringing all this data together, we have techniques like ETL, where we extract, transform, and load the data into a new place, and ELT, which does the loading first, then transforms it within the destination system. Finally, there's data virtualization, which is essentially creating logical views of data without needing to move it around, offering a really flexible way to combine information from many sources. Okay, let's talk about how REST API and gRPC fit into the world of data engineering. REST is a really common way to build interfaces for your data pipelines. It's simple, scalable, and lots of developers know how to use it. Think of it like ordering food online. You make requests, get, send information, post, update things, put, or delete them, delete all using standard methods. Now, gRPC is a newer technology that's gaining serious traction. It's essentially a much faster way to communicate data between systems because it uses binary messages instead of text-based JSON. And thanks to its strong typing through protocol buffers, you get really good consistency in your data. It's a bit more complex initially, but offers significant performance benefits, especially when dealing with large volumes of data. Okay, so let's talk about combining data from different places. Think of a company with sales data in one database, customer information in another, and product details spread across several systems. That can be really tricky to work with. Data federation and virtualization are strategies that help us solve this. Federation is like creating a single window into all those separate databases, allowing you to query them as if they were one big system. It's all based on understanding how the data is stored and what it means. Then we have visualization, which presents a simplified, consistent view of the data without actually moving or copying any of the original information. It's like creating a virtual database experience sitting on top of your existing sources. Okay, so in data engineering, we're increasingly seeing event-driven architectures gaining traction. Think of it like this: instead of one part of your system telling another exactly what to do at a specific time, you're reacting to things as the asterisk happen asterisk. When something changes, let's say a new record is added to a database or a sensor reading updates, an event is triggered. That event gets sent to a central hub, often called an event bus or broker like Kafka or RabbitMQ. Then, different services, the consumers, listen for those specific events and do what they need to do in response. This makes your system much more scalable because components are independent of each other and it's easier to adapt to new requirements. Okay, let's talk about a really powerful concept in data engineering: immutable data patterns. Basically, instead of changing our existing data, which can be tricky and prone to errors, we create completely new versions when we need to make changes. Think of it like making a photocopy rather than rewriting the original document. This helps us keep track of exactly what happened to our data at any point in time, makes debugging much easier, and builds a lot more confidence that everything is working as expected. Okay, let's talk about change data capture, or CDC. Basically, it's a way to keep your databases perfectly synchronized with other systems, like when you need to update analytics dashboards in real time. Instead of waiting for a scheduled batch process, CDC continuously monitors the database for any changes, new records, updates, even deletions. There are a few different ways to do this, from using triggers within the database itself to analyzing transaction logs. It's becoming increasingly important for modern applications that demand quick and consistent data. Okay, let's talk about keeping up with the flow of data. We're looking at streaming joins, essentially joining streams as they come in, instead of waiting for a big batch job. Think real-time insights. And then we have window functions. These are like calculating things across groups of records within a stream, not just individual rows. It's super useful for things like rolling averages or comparing your current activity to what you've done before. Really powerful stuff when combined with those streaming joins. Okay, let's talk about deduplication and reconciliation, two key players in keeping your data clean and consistent. Think of deduplication as a way to find and eliminate duplicates within your data. There are different ways to do this, from simple exact matches to clever fuzzy matching that can spot records that look similar even if they aren't identical. Then comes reconciliation. This is all about resolving disagreements you might find when comparing data from different sources. Maybe a customer has slightly different address information in your CRM versus your billing system. It's not just about finding duplicates, it's about making sure everything aligns and makes sense, and that often involves careful review and some smart rules. Let's talk about getting your awesome data engineering work into the hands of business users. One really important step is connecting those pipelines you build to tools like Tableau or Power BI. Think of these as super easy ways for people to explore and understand their data, no coding required. The first thing you'll do is connect to your data warehouse, whether it's Snowflake, Redshift, or BigQuery. Then, you might need to do some quick transformations in the BI tool itself, but often it's better to handle more complex changes within your engineering pipeline. Finally, it's all about building those dashboards and reports using the amazing visualization features of Tableau or Power BI to make data stories shine. Let's talk about how data engineering helps unlock the full potential of data science. Think of it like this: data scientists are the architects designing amazing buildings with data, but they need a strong foundation, and that's where data engineers come in. They build the pipelines to get the raw materials, the data, into shape, creating efficient warehouses or lakehouses so the data scientists can easily access and work with it. Essentially, data engineering removes the tedious tasks of data collection and cleaning, allowing data scientists to concentrate on actually building models and finding valuable insights. Okay, so let's talk about how we make really big data sets easier to work with. We're going to cover data marts and aggregation, essentially how we create focused snapshots of information for specific teams or analyses. Data marts are like smaller, specialized versions of a broader data warehouse, designed exactly for what a particular department needs. They're much faster to query and help users get straight to the relevant insights. And then we'll discuss aggregation, which is all about taking raw data and summarizing it into key metrics like totals or averages. Techniques include summarization, rolling up data at different levels of detail, and a common design called the star schema that helps organize everything effectively. Let's talk about how Delta Lake, Iceberg, and Hudi are changing the game for data lakes. Think of them as layers building on top of Parquet files, providing reliability, consistency, and powerful features you wouldn't normally get in a traditional data lake. Delta Lake adds crucial ACID transactions, making your data more trustworthy. Iceberg focuses on handling massive datasets with efficient metadata management and schema evolution. And Hudi is really strong at handling changes within the lake, especially when dealing with upsets and deletes. It's optimized for incremental processing. As you can see in this table, they all offer time travel, but each has different strengths and weaknesses depending on your specific needs. Okay, let's talk about data compaction and cleanup, a really important step in the data engineering process. Think of it like tidying up your room. You want to get rid of things you don't need and organize what you do. We use techniques like deduplication to find and remove duplicate records, archiving older data that isn't used as often to save on space, optimizing data types to be more efficient, and partitioning or clustering your data for faster querying. It might seem small, but these practices significantly improve performance, lower storage costs, and make your entire system much easier to manage. Okay, let's talk about slowly changing dimensions, or SCDs. Think of dimension tables as snapshots of important entities like customers, products, or locations. But these things change over time, right? A customer might move, a product's description could be updated, or a store might close. SCD are all about how we handle those changes in our data warehouse. We have different approaches. Type 1 adds a new row for each change, keeping the old version intact. Type 2 simply overwrites the existing row, which is good if you only care about the current state. And then there's Type 3, which is a hybrid that combines elements of both. It's all about picking the right strategy based on what your business needs and how you want to analyze historical trends. Okay, let's talk about getting those SQL queries running smoothly. That means optimizing them. A slow query can really bog down your entire data pipeline. The good news is there are a lot of things you can do. First, indexing can drastically speed up lookups on frequently used columns. Then, we want to simplify our queries. Sometimes rewriting them from scratch can help. Don't forget about choosing the right data types. Using an integer when you can use a string saves space and processing time. And finally, understanding how your database is actually executing the query using tools like explain gives you insights into bottlenecks. Let's talk about how we can make querying our data faster. We'll look at partitioning, bucketing, and indexing, all clever ways to organize your tables so that when you run a query, it only has to scan the relevant parts of the data. Partitioning divides your table into separate files based on certain values, like dates or regions. Think of it as sorting your books by category. Then there's bucketing, which uses hash functions to put similar records together in their own files. Finally, indexing creates a quick lookup guide for frequently queried columns, speeding up searches but potentially slowing down writes. Okay, so when we're dealing with data, we need to think about how it's stored and moved around. We have a bunch of different file formats, things like CSV for simple tables, JSON for more complex structures, Parquet, which is awesome for analytics because it stores data in columns efficiently, and Avro, which is really useful when working with Hadoop. But just storing files isn't always enough. We also want to make them smaller so they take up less space and transfer faster. That's where compression comes in. We have algorithms like Snappy, gzip, and ZSTD. Each has its own strengths and weaknesses. Snappy is generally fast and offers a decent balance between speed and size reduction. Gzip is pretty common for text files, but it's not as speedy as the others. And then there's the STD, which is really gaining popularity because it compresses data incredibly well while still being relatively quick. Okay, let's talk about a really important consideration in data engineering: the balance between latency and throughput. Essentially, we're trying to figure out whether we need our system to react super quickly, like with something that needs real-time decisions, or if we just need to move a massive amount of data around, like for reporting and analytics. You'll often find you can't have both at the absolute highest level. Increasing speed means processing less data at once, and increasing the volume processed means it takes longer to handle each individual piece. There are different approaches, things like batch processing, where we're happy to wait a little for more data, versus stream processing that needs immediate responses, even if it means handling slightly fewer records at any given time. And sometimes, clever techniques like caching and buffering can help us find a sweet spot. Okay, let's talk about how we make sure our data pipelines are working correctly. Building a reliable system starts with rigorous testing. We have several strategies, starting with unit tests, which focus on individual parts of the pipeline like transformations or connections. Then we move to integration tests to check if everything works together smoothly. End-to-end tests simulate a real user's experience, ensuring the whole process is valid. Crucially, we also need data quality checks, making sure the data is complete, accurate, and consistent at every step. We'll use schema validation to confirm that data fits expected formats and consider statistical testing for any unexpected anomalies. Okay, let's talk about ensuring our data is reliable. We're starting with data profiling. Think of it as a deep dive into your datasets. It helps us understand exactly what we're working with, the types of information, how much missing data there is, and even the distribution of values within each column. Then, we move on to anomaly detection, which is all about finding those unexpected or unusual points in our data, things that just don't fit the pattern. We can use statistical methods or even machine learning models to spot these anomalies, helping us catch errors and potential problems before they cause issues downstream. Let's talk about API gateways. They're a really important piece of the data engineering puzzle. Basically, an API gateway is like the front door to your entire data ecosystem. It handles all incoming requests and makes sure they get to the right place securely and efficiently. It can route requests to different backend services, verify who's asking for the data, protect against too many requests at once, and even transform the data slightly if needed. Think of it as a smart intermediary that simplifies your data access. Okay, let's talk about how we can build really strong data pipelines. Often, instead of one giant system, a monolith, we're moving towards breaking things down into smaller pieces called microservices. Think of it like building with Lego bricks versus sculpting from a single block. It's much more flexible. Microservices let us scale each part independently, and they can recover easier if something goes wrong. Data integration is key here, especially when data is spread out across these different services. We're seeing patterns like using message queues to keep things talking smoothly, and tools that capture changes in one system and automatically update others. It's all about making sure information flows reliably. Okay, let's talk about scheduling and how jobs fit together in data pipelines. Think of it like a chain reaction. Each step needs to finish before the next can begin. We use tools called scheduling engines, like Airflow or Prefect, to manage this. They figure out when each job should run based on its dependencies. Dependencies are simply relationships job A has to complete before job B starts. It's all about making sure everything runs smoothly and in the right order. Okay, so let's shift gears and look at event-driven ETL. Traditionally, we'd set up scheduled jobs to pull data regularly. But what if the data is constantly changing? That's where event-driven pipelines come in. It starts with an asterisk event. Asterisk, think of it like a notification saying something has changed. This could be anything from a sensor reading to a new order placed. These events are sent to an event broker, which is essentially a buffer that holds everything. Then, ETL jobs, our data transformation processes, listen for these events and react immediately by cleaning the data, adding context, or combining it with other information. Finally, this processed data gets stored in its final destination. The big advantage here is speed and agility. You're not waiting around for a schedule. The pipeline responds to changes as they happen. Okay, let's talk about getting data flowing smoothly between different systems. It's not just about dumping information somewhere, it's about making sure that happens reliably and efficiently. We call this orchestration. Basically, we need tools to manage the whole process. You'll have your data pipelines, which are essentially the steps involved in moving and transforming the data. Then you need an orchestrator, something like Airflow or step functions, to automate all of those pipelines. And finally, it's critical to schedule these things and constantly monitor them so that if anything goes wrong, you know about it immediately. Okay, let's talk about keeping a close eye on cloud costs in data engineering. It's super common for teams to end up spending way more than they should because of things like over-provisioning resources or leaving instances running when they're not being used. There are definitely some challenges. Often it's hard to see exactly where the money is going, especially across all the different cloud services you might be using. But don't worry, there are strategies. We can right-size our instances, take advantage of spot instances for discounts, and use tagging to track costs accurately. And automating shutdowns during off-IOs is a simple way to save big. Okay, let's talk about SICK, continuous integration and continuous delivery, and how it applies to our data pipelines. Think of it as a way to automatically build, test, and release our data transformations. CI focuses on getting code changes merged frequently and running automated tests to catch problems early on. Then CD takes that tested code and automates the entire deployment process, from building the code all the way through deploying the pipeline itself. This is really important for data because it ensures high quality, gets us data faster, minimizes mistakes, and lets us quickly make changes without huge manual effort. It's about making sure our data pipelines are reliable and always delivering what they should. Okay, so let's talk about keeping your data safe. Data privacy is a huge part of data engineering. We've got several ways to handle sensitive information. Basically, we want to protect it while still being able to use it for analysis. One common technique is tokenization, where you replace real values with random substitutes. Redaction removes specific bits of info, like masking parts of an email address. Encryption scrambles the data entirely, and pseudonymization replaces identifiers with aliases that are linked together. Now, there's also a whole category of advanced techniques called PET privacy enhancing technologies like differential privacy, which adds a bit of noise to protect individuals, and homomorphic encryption, which lets you do calculations on encrypted data without ever seeing the original numbers. Essentially, we're balancing utility with security. Let's talk about ensuring your data is actually good. Manually checking everything would take forever, and, let's be honest, we all make mistakes. So, the goal here is to automate those checks. We start by profiling our data, basically getting a really good understanding of what it looks like. Then we set up rules, like this field must have a value or numbers in this column should be between 1 and 100. Tools like Great Expectations can help us build these automated checks into our pipelines so they run automatically every time new data arrives. Think of it as building an early warning system. If something's not right, the process stops and someone gets alerted. Okay, let's talk about keeping your data consistent, a really important part of data engineering. We're focusing on two key concepts, snapshotting and version control. Snapshotting is like taking a picture of your data at a specific point in time. We capture a read-only copy to preserve that state. Then we use version control systems like Git to track all the changes made to our pipelines and transformations. This allows us to go back to previous versions if needed, which is fantastic for reproducibility, auditing, and working with teams effectively. Tools like DVC can really help you manage this process at scale. Okay, let's talk about data mesh. It's a really interesting shift in how we think about data. Instead of having one big team handle all the data, the idea is that each business domain like marketing, sales, or operations takes ownership of their own data. They treat it as a product, with clear interfaces and standards. There's also a shared infrastructure to make this happen, but domains have a lot of freedom to do things their way, guided by some common rules. It's about breaking down silos and making sure the right teams are closest to the data they need. Okay, so let's talk about the modern data stack. It's all about building a system that can handle massive amounts of data efficiently. Think of it as a pipeline starting with your different sources like databases or even apps you use every day. We then need a way to get the data into a central place for storage, usually something powerful like Snowflake or BigQuery. Next, we transform the raw data using tools like dbt and Spark to make it clean and ready for analysis. Finally, we visualize the insights with tools like Looker or Tableau to actually understand what's happening. Okay, let's talk about keeping an eye on our data pipelines. It's all about observability. Think of it as having a detective in the background ensuring everything is running smoothly. Why is this important? Well, we want to catch problems before they cause real issues for our users and quickly figure out what went wrong if something does happen. We use metrics like latency and throughput, logs that detail specific events, and traces that follow data as it flows through the entire pipeline. Tools like Prometheus, ELKstack, and Jaeger can really help us with this. Okay, let's talk about moving beyond just one cloud provider. Building a multi-cloud data architecture can be really powerful. It gives you a lot more flexibility and helps protect against disruptions. You'll want to think about where your data actually needs to be located based on how it will be used, and also consider avoiding getting locked into any single vendor. There are several patterns we can use, like keeping some data on premises while using other clouds for specific tasks, or running the same workloads across multiple clouds for ultimate reliability. And of course, cost optimization is a big factor. You might find different providers have better pricing for certain services. Don't forget about ensuring that your data stays consistent across all those environments. Things like change data capture can help with that. Okay, let's talk about data democratization and self-service analytics. Essentially, we're shifting the power to access and understand data away from a small group of specialists, the data engineers, and spreading it out across the entire organization. Think of it as giving everyone the tools they need to ask questions and find answers directly within the data. We use things like data catalogs to make it easy to discover what datasets are available, self-service BI tools so people can build their own reports without needing to be coding experts, and strong data governance practices to ensure that the information we're using is trustworthy. The goal is a more agile organization where decisions are based on real insights, not just estimates. Okay, let's talk about data fabrics. For a long time, we built data systems like separate islands, each team managing their own databases and often with completely different ways of looking at the same information. This created huge problems with consistency and made it incredibly difficult to get a holistic view of our business. A data fabric is all about changing that. It's a modern approach that focuses on decentralization, meaning data governance isn't just managed from one central place. Policies are applied where the data actually lives. Then there's federated access. Users can grab the information they need exactly where it resides, not having to wade through a central repository. And finally, the concept of a data mesh really shines here, giving ownership and responsibility for specific data domains directly to the teams who understand those areas best. Let's talk about graph databases. Instead of thinking about data in tables like you might with a relational database, they organize information around connections, nodes, and their links to each other. Think of it like a network of people and how they know each other. Graph databases are really powerful for problems where those relationships matter most, like figuring out what products customers might be interested in or spotting fraudulent activity. Neo4j and Amazon Neptune are two popular options you'll often hear about. Let's talk about streaming analytics. It's a big shift from how we used to handle data. Instead of waiting for huge batches, we're looking at things as they happen. Think of it like this. You have continuous streams of information coming in, and streaming platforms let us jump right into analyzing that data immediately. We use things like message queues to keep everything organized, stream processing engines to actually do something with the data while it's moving, and real-time databases so we can quickly grab those insights when we need them. Okay, let's talk about building a complete data platform. It's not just one thing, it's a whole ecosystem. We start with the sources where our data lives, which could be anything from databases to streaming services. Then we need an ingestion layer to pull the data in and load it somewhere. We choose a storage solution, often a data lake for raw data and a data warehouse for structured information. Next comes processing, cleaning, transforming, and preparing the data. Finally, the serving layer makes all of this accessible for reporting, analytics, and actually using the insights we've gained. Thank you for watching.